This video is on spin coupling in proton NMR. When two atoms are affected by a magnetic field, they can also have an effect on each other if they are close enough. With respect to protons, this means if they are geminal or vicinal. As long as the protons are in two different chemical environments, they are very likely to couple with each other. So let's take this structure here. Let's say we have these two protons coupling with each other. Proton A is coupling with proton X. Proton A will be split into n+1 peaks, where n is the number of protons that are coupling in that same environment, i.e. the number of HX's. In this case, as we only have one HX, it means we will get one split, giving us two peaks for HA. Now if we look at HX, it is being coupled by HA. As there is only one HA, we'll get a n+1, n equals 1, so 2 peaks for HX also. When you have 2 peaks for a single environment, you refer to it as a doublet. So we would say that both HA and HX appear as doublets on this NMR spectrum. The amount the peaks split is referred to as the coupling constant, or term J, and is very specific to whatever two protons are coupling. So if you have multiple splits in a system, you can associate coupling constants with specific protons in specific environments. Now let's look at this other molecule. We have two HX's and one HA. How many peaks do we expect to see for HA, and how many peaks do we expect to see for HX? Well, HA will be coupled with the HX's. There are two HX's, so n equals 2. So we would expect HA to have 3 peaks. 2 plus 1 is 3, of course. We would refer to this peak as a triplet. The HX's, on the other hand, would still only be coupled to the single HA, and therefore would form a doublet. N equals 1, 1 plus 1 equals 2, you get 2 peaks. Of course, as we remember from the previous video, if we were to integrate these peaks, we would still obtain a 2-to-1 ratio, with the HX being 2, HA being 1. Even though the peaks split, the overall area under the peaks stays the same. This coupling is extremely useful as we can determine what fragments of the molecule are connected to what parts. Say, if we have a triplet, we know that that must be next to a carbon with 2 hydrogens. This allows us to figure out the constitutional isomer that we are looking at. How many peaks would you expect to see in this molecule? What kind of coupling pattern would you expect on these protons? Have a go and draw the expected NMR spectrum that you would see. Feel free to use the cheat sheet to figure out the chemical shifts. You may pause now. And here is the spectrum. As we can see, the methyl bonded to the oxygen appears as a singlet because there is no protons to couple with. However, the protons in the two environments of the ethyl group appear split because they are coupled. The protons on the terminal carbon appearing as a triplet, and the protons on the secondary carbon appearing as a quartet, as they are being split by 3 protons. When it comes to NMR, the one thing you do have to be careful with is symmetry. For example, this para-xylene only has 2 distinct environments, and therefore will only appear as 2 peaks on an NMR. As we only get the relative amounts of the protons, we will see a 3-to-2 ratio of our peaks, even though in fact there are 6 protons on the methyls, 4 protons on the ring. Symmetry makes your molecules seem simpler than they are.